Okay, so this is a quick recap on what we've done so far on computer systems. Now we've covered software, logic gates, the CPU and hardware in general. So let's have a look, see what we've actually got. So firstly, software and hardware in comparison. So hardware, we generally say anything you can touch. You've got the exam board, what they like, up there as well. So electrical and mechanical components which make up a computer system. So yes, anything you can touch is a good rule of thumb. However, that does also include your cat, which tends not to be considered hardware. Now when you're in an exam, don't try to be too clever. Keyboard and mice are awesome examples of hardware. Whilst I'm sure you've got all sorts of weird and wonderful bits of hardware, if the examiner doesn't know it, then chances are you're not getting the mark. So make sure you're being obvious. With software, so that's the program that is running on the hardware. You got to think the basic things like word processors. Again, try not to be too fancy. And also you'll notice on the examples, I've not used brand names. That is deliberate. The last mark scheme which I looked at, which had this sort of question, it did say don't give any credit for brand names. So if it said name 3 bits of software and you said Word, Excel, and then a computer game, then you wouldn't get any marks. So try and keep it generic. If you want to say word processing software such as Microsoft Word, fine. But try and make sure you're clear on what you're trying to say. Okay, so software is split down into a couple of sections. You got system software and you got application software. The differentiation that I would like is system software is what helps you do the tasks. Application software is what you'd buy a computer for. So you may buy a computer to use Word. You may buy a computer to use Internet Explorer if you're misguided. Alternatively, you'd use a decent web browser. You wouldn't buy a computer in order to use Windows. You wouldn't buy a computer in order to use compression software. Yes, you may want to compress files in order to do this, that, and the other, but that's not the purpose for you buying that computer. So application is what you're buying the computer for, the main purpose that you're using the computer for. System software is again broken down into 2 parts. You got the operating system, so Windows, Linux, Android, iOS, macOS, all sorts of things. And you've got utility software. Now the utility software is just things to help make your life easier, such as disk defragmentation, if your hard drive is getting clogged, encryption stuff, so you can encrypt files or encrypt things as you're sending them, compression, so zipping up files. Back in my day, it used to be done by a totally separate program. Now it's baked into the operating system, but it's still utility software, still there helping you to do what you need to do, but it's not why you'd buy a computer. The operating system we still try to think of as the core functionality of it, rather than all these extra things which are bundled with it. So you've also got backup software and the file browser, so files, so you can actually access all your documents. Okay, so that brings us to the operating system. The operating system has several key components, several things which it's trying to do. One of those is memory management. So you've got 4 gig of RAM, hypothetically, or you may actually have a decent computer, and that RAM is being used by the programs which are being run. Now, if you've got multiple programs running, how is it deciding which processes get which bit of memory? So that's where the memory management part of the operating system comes in, and that will decide how to do things. And it will also make sure that one program doesn't accidentally start using another program's memory, because that can cause security vulnerabilities. Some of them are known as buffer overflow attacks. You got processor management. So let's say you've got a single core, single processor setup. You got two programs running. The CPU has to organize when is each of the programs going to be using the CPU, and sort of saying, okay, that one's turn, now that one's turn, and so on. I/O devices, the input-output devices. If you've bought any computer hardware, you may find that it comes with a disk. That disk, it was more the case in days gone by. Now a lot of it is bundled into the operating system, or it's automatically downloading it from the internet when you plug it in. But it was always the case that you need that disk in order to install the drivers, so the operating system knows what this bit of hardware which you're installing is. For example, if you bought an operating system 3 years ago, you've bought a new printer, it doesn't necessarily know, the operating system doesn't necessarily know what this new bit of kit is and how to interface with it. So that's what the device drivers will do. They'll fit into the operating system and help translate and communicate between the operating system and the new device. Now, application management to me is things like add remove programs, installers, the app stores, things like that. The exam board tend to go more on the application management. So is this user allowed to use that application? Security, you've got things like antivirus and firewall, but you've also got the login screen and things like that. So ways of keeping your computer safe. Okay, so that's your software, but where is that software actually stored? Well, you got the RAM, also known as memory or primary storage, or you've got the storage, also known as secondary storage, or your hard drive or your solid state drive. Now, your secondary storage is where your programs and your software are stored. When you run them, it goes into RAM, which is your working memory. So your secondary storage is permanent, so if you turn off your computer, you're not going to be losing whatever you've installed, but you will lose your current save data. So if you're playing a game, have a power cut, that latest data before the save is lost. That's because that bit is in RAM, which is volatile, which means it will lose its contents when the power goes. So all the running programs, so as soon as you load up a game, it goes into RAM, and that's where it's being run from. And it's a lot faster than the secondary storage because it's a lot closer to CPU, a lot more expensive memory, which is why you may have a couple of terabytes of secondary storage and only a few gigabytes of RAM. Okay, so a quick note on computers. You no doubt have a computer of some sort, and that computer, chances are any program you download will be able to run on it. Therefore, it's a general purpose machine. You can run pretty much whatever you want on there. If you think back into the early days of computing, you'll get these huge, great computers which may be specialized only to do one thing, such as cracking an enemy military code or doing short equations, or just counting things. So one of the early computers was just a counting device. Now these are specific single purpose or fixed program machines, as opposed to what you're running, which is a general purpose machine. It runs basically whatever you write for it. Whatever program somebody has done, it will say, hey, try this program, and it will run that. So you also in your house have some embedded computers. Now they're not general purpose. They're doing a single task. They're doing a single thing. An example of that would probably be your microwave or your washing machine. It's got a computer in there, a really simple one, and it's programmed in the factory to do one thing: heat up your food. May have different settings, but you're not changing the software on there. You're not going to be downloading a different program to run on your microwave. So it's built into the device, and it's for a specific or dedicated purpose. So those are the two things you need to know about embedded computers. They're for a dedicated purpose, and it's built into a product. Again, if you're giving examples, be obvious. Washing machines and microwaves are awesome examples. Now, if you look under the hood, how they work is slightly different. So the von Neumann architecture is what your computer is using. This is what general purpose computers are using. So you've got your RAM, which when you run a program, that program gets loaded into RAM along with any data with it. So your computer game will be stored in the RAM along with the save games. So Microsoft Word may be stored in RAM along with your document which isn't yet saved. Your Python program is loaded into RAM along with all the variables. And then the CPU can access that RAM backward and forward, and get all the data and all the rest. Now, this is really useful because it means it's really easy to change the program. It makes it so it's a general purpose computer, and you can download new programs, load it into the RAM. Hey, you've got a different function for your computer. Can potentially cause issues in that if something manages to write to the wrong area, your best case, get a crash, worst case, have a vulnerability and be compromised. Now the alternative is what's known as the Harvard architecture, and that's got the instructions separately. So you'll find this in embedded devices where they've programmed the device to do a specific thing, and that will be held in read-only memory. So your program for your washing machine or your microwave is held in ROM because it will never need to be changed. If you had that on your home computer, you never were able to change the program, it would mean something horrible like whenever you boot up your computer, it loads up Fortnite, and nobody wants that. You can still have RAM on an embedded device. Chances are it's a lot smaller. You'd only really need a few K because you're really not storing that much information. Maybe what mode the microwave is on or something like that. Okay, so we mentioned the CPU and the RAM. And what we're concerned with at the moment is the von Neumann architecture. A quick note on that whilst we're on it. There's a YouTube link there, and I'll send that over to you as well. But that goes to that page, which is a nice computer file video on von Neumann Architecture, and the chap von Neumann, who apparently was a really cool chap. It's worth having a look at and seeing what it's all about and who this guy was that came up with the basic ideas of how the computer should be structured. Okay, so this is the main one. This is what we're interested in, the von Neumann one, because that's what your computer's doing. The embedded systems, you'll need to know those, but we don't go into too much more detail. Okay, so you got the CPU and the RAM. The RAM is where all your programs are loaded into, so as soon as you double click on something, it will go into RAM, and that's your working memory. So I usually take the RAM and the secondary storage, the RAM to be your desk and the secondary storage to be a filing cabinet or your bag. If you want to run anything, if you want to work on anything, it needs to go onto your desk, it needs to be in the RAM. Whereas when you finish with something and you want to store it, it can go in your bag or the filing cabinet. Now, CPU is composed of several parts. You've got the control unit, which, funnily enough, controls the computer. It does things like contains the clock, it says what should be done, and coordinates everything. Now, the clock is just a pulse. That pulse is going at a regular interval, and that's keeping the entire computer on beat. So everything will happen when the clock pulses. Now that will be quite a few times a second, and that's your 3 gigahertz or whatever, means that it's pulsing that many times a second. You got the arithmetic logic unit, and that does mathematical calculations. It does logical comparisons, so is this greater than that? And it does logic operators such as and this and that, and binary shifts, so it does the low level mathematical calculations. Then you got the buses, which is just how the different parts of the computer communicate. Those are the little tracks which are on the computers, which allow everything to communicate. And in the CPU, you've got some really fast ones, allowing those to communicate. Now, on the next link, it's this page, which is a really nice page which looks at a CPU, and you can run a program on this and go through all the steps. So you can see here you've got the CPU, here you've got the RAM, and the CPU has the different aspects, so the ALU and the control unit, which is controlling everything. It's worth having a look at that page and having a tinker, see what you can find with it. Okay, so we've looked at what the hardware is inside it. We've also got, okay, how does it actually go through? And that link which I've just showed you is awesome at showing this. First, it's going to fetch the instruction from the RAM. So it looks for where the next instruction is, grabs that, brings it into the CPU. The decode part is where it looks at that operator, looks at that command and says, okay, what does that actually mean? What needs to be done with this? And then the execute aspect is where it actually does what the command says, which may be reading and writing from main memory. And the points on this slide are all the things which the exam board will give you marks for. So it will go through that cycle, then it will just start again, and it will keep going through that cycle again and again and again, however many billion times a second. Okay, that's the CPU. And now we can look at things for more of an electronic side. The computer, if you look at it at a lower level, is made up of transistors and capacitors. Those transistors and capacitors make up logic gates, and with those logic gates we make a computer, or we make a system of some sort. Now there's a few more logic gates than just these, but these are the ones which you need to know for your exam. You've got the NOT gate, which will just inverse whatever the input is. So if you've got a 1 coming in on here, so power or true or whatever, then it will flip it so it becomes a false. If you got a false coming in here, then you'll get a true coming out. With an AND, if you've got a true and a true, then it will come out true, otherwise it will be a false. Now when I'm unsure on any of these, I try to put it into a sentence. If it's sunny and I've got a football, I'll go to the park. Okay, if I don't have a football, am I going to go to the park regardless of whether it's sunny or not? So I like to put it in that. However, if you use the sentence, if it's sunny or I've got a football, I'm going to the park, you could well end up playing football in the rain. So with an OR, if either one of the inputs is a 1, then it will come out as true. Now we got some more nice links. The first one is this page, and I went to the bottom and just did the example. And this one shows the gate. So you've got an AND gate, you got an OR gate. You do have some other ones which we're not really concerned about, and OR and not the ones we want. So with an OR gate, you got these two are off, so the light is off. Turn one of them on, the light comes on. If they're both on, the light's still on. If one of them's off, the light's still off. If they're both off, then the light's off. Whereas with an AND, individually they do nothing. If they're both on, then it will come on. And with a NOT, it's just the opposite. Another nice link is this page, and on this one it does, apart from showing you all the logic gate, it does also have a little test. So if you're going through this, and this is a pretty good example of what you'll get in an exam. So that's a perfect example. As okay, if you got 0 coming on that wire, 1 coming on there, okay, 0 or 1, so that's going to be a 1, and you got a 0 coming on there, 0 into a NOT will become a 1, so we got a 1 and a 1 going into an AND, so that makes it a 1. So we click on that, do a 1, and we can check the answer. There we go, we got that right. So have a look at that website, have a go at a few of those. And obviously logic gates made out of dominoes, because why wouldn't you? And this chap has also, no, I haven't got it loaded up, has also done an entire domino computer, which is a fantastic feat. It looks really cool. It's well worth looking up, and I believe you should have already seen that video, but it's an interesting watch. And all it's doing is simulating logic gates out of dominoes. Okay, so you do need to know some of the truth tables for these, and this is the overview. So if it's 0, 0, it'll be 1, 1, 1s go to 0, so that's your NOT. An AND is only a 1 if both of the inputs are 1s, and an OR is a 1 all the time apart from when you've got 2 zeros. It's worth noting that the inputs A and B are listed in numerical order. 0, 0 from binary is 0, 0, 1 binary is 1, 1, 0 is 2, 1, 1 is 3. So because they've put it in order, you know that you're never going to miss one, and it's a nice pattern. So always try to make sure you're doing any truth tables in order, particularly if you have a C input in there as well. So if we have a look at this one, you'll notice this is also in order. So you've got 0, 1, 2, 3, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, 1, 1, 1 is 7. So because it's all in order, we know that we've got every single one, and we're not going to miss one because we're doing things and trying to guess which one we're missing. Okay, so that's your overview. Hopefully that covers some of the main things that you need, and we'll be moving on to the next sections shortly.